Okay, in this video, we're going to use the node voltage method to find the current IO, which is the current flowing through this voltage source. Now think about it, right? Before we even do anything, we know we have to use more than the node voltage method because we have a current that's going to be flowing through a voltage source and only this voltage source, which means we have to use KCL at some point in analyzing this particular circuit, because that will be the only way to calculate the current flowing through this 12-volt source. Now let's begin. We know the first step is to always identify the essential nodes. But we know this is an essential node. I'm going to call that node 1. This is another essential node. I'm going to call it node 2. This one as well. I'm going to call it node 3. And we know we have an essential node at the bottom here. So I'm just going to call it node 4, but I'm actually going to take it as the reference. So I'm going to take this node as the reference, right? Now let's begin to write the node voltage equations starting at node 1, right? So they want us to write the node voltage equation for node 1. They want us to find the voltage at node 1. Well, when we look at this, we know that we have this voltage source in a single branch by itself, which means the value of this voltage source is going to be the value of the voltage at node 1. Therefore, we know V1, which is the voltage at node 1, is going to equal a positive 12 volts because of the polarity of this voltage source. So V1, which is the voltage at node 1, equals 12 volts. Now, this is not our answer, but I'm just going to circle it because it might be helpful to us, right? So we know V1 equals 12. Now let's move on to node 2. We want to use node voltage to find the voltage at node 2. So I'm going to write this as node voltage at node 2. Remember, we're always going to assume the current is leaving a node. So we're going to assume the current is going in these directions. Okay? So when we look at this, we actually have a current source that's going to be entering this node, which means instead of it being a positive current, we're just going to take it as a negative current. So we're going to have negative 2 times 10 to the negative 3 plus we have this current source that's also entering this node. So we're going to treat it as a negative current. We have negative 4 times 10 to the negative 3 plus, and finally we have this current going in this direction right here. So we're going to have V2 minus the ground node, which we know is just going to be 0. So we can say V2 over 2000. V2 over 2000. And all of that must equal 0. So when we start to simplify this now, we know we're going to multiply each term by 2000 to get rid of this 2000 in the denominator here. So when we multiply 2000 by the first term, that's going to give us negative 4. 2000 times this term is going to give us negative 8 plus V2 equals 0. Therefore, V2 equals 12 volts. So we also know the voltage at node 2, and that's going to be 12 volts. So we know the voltage at V1. We know the voltage at V2. So let's find the voltage at node 3 now, right? So we want the voltage at node 3. So because we don't have any voltage source in a branch by itself, we're just going to write the node voltage equation. So we have node voltage at node 3. So we're going to assume the current is leaving this node. So we're going to have a current going this way, and this way. So we're going to have a positive current, right? Because we have this current source that's actually leaving and going in this direction. So we're going to say that's a positive 4 times 10 to the negative 3 plus we have the current flowing in this direction here. So we're going to take the difference in voltages between V3 and V1 and divide it by 2000. So we're going to have V3 minus V1 divided by 2000 plus we're going to have V3 over 2000, right? So V3 over 2000, and all of that equals 0. We're going to multiply each of the terms by 2000 to get rid of this 2000 here. So when we do that, that's going to give us 8 plus V3 minus V1 plus V3 equals 0. We know the value of V1 because we know we have this voltage source that's going to give us the value of V1. So we can just substitute in 12 for V1. Therefore, we're going to have 8 plus 2V3 minus 12 equals 0. So we're going to be left with 2V3 equals positive 4. So V3 equals 2 volts. Now this is not our answer, but this is the voltage at node 3, right? So we know the voltages at each node. Now they want us to find the current in this branch, the current that's going to be flowing through this 12 volt source. Now there are a few ways we can go about this. What I'm going to do is I'm actually just going to find the current flowing in this resistor here and then use KCL at node 1 to find the current IO, okay? Now I'm going to assume, right? I'm just going to assume that the current is going to leave this node in this direction. I'm not sure, but I'm just going to make that assumption. So because it's going to flow in this direction, we know it's going to flow into the positive terminal and then into the negative terminal. So to find the current, let me label the current I sub 1. So we're going to have a current I sub 1 that's going to flow in this direction. So to find I1, I1 equals, we're going to have V1 minus V3 divided by 2000. V1 minus V3 divided by 2000. We know the value of I1 is going to be 12 volts. So we have 12 minus 2 divided by 2000. Therefore, I1 equals 10 divided by 2000. 10 divided by 2000. When you put that in your calculator, that's going to give you I1 equals 5 milliamps. So we know the value of the current I1, which is the current flowing through this resistor here. So we're just going to take KCL at node 1, which is going to be right here, right? So we're going to take KCL at node 1. When we perform KCL at node 1, we know the current that's going to be entering this node is just going to be the current I0, right? So we're going to say KCL at node 1. We know we have I0 that's going to be entering that node. And the currents leaving is going to be this current I1 and this 2 milliamp of current. So we're going to have equals I1 plus 2 milliamp. Now we just found the current I1 and that's going to be 5 milliamps. So I0 equals 5 milliamps plus 2 milliamps. Therefore the current I0 equals 7 milliamps. So the current I0 is going to equal 7 milliamps, and this is going to be our answer for this particular problem. I0, which is the current flowing through this voltage source, is going to be 7 milliamps.